By now, you should have completed the programming challenge to get the Site Geo search working. You should be able to enter coordinates, plus a radius, and the map should update like so. What we want to do next is enable this excess capacity filter working with the GeoQuery, and this requires a few refinements to our code. Recall that earlier on, we built a site capacity leaderboard. Underlying this leaderboard is a sorted set that can get us the current capacity of each site. We can use this together with the GeoQuery from the previous unit. How do we do that? Let's look at some pseudocode. First, we'll perform our query using the georadius command. This will get us a set of 0 or more site IDs. We'll iterate over these IDs, checking the score for each site ID against the capacity sorted set using the zscore command. If the capacity is greater than our chosen threshold, we'll add the site to the query result. In essence, we're joining a GeoQuery with a sorted set query. Now, whenever we're combining Redis commands in this way, we need to think about the performance implications. It's always best to start looking at the time complexity of the Redis commands in question on the redis.io documentation pages. So here we see that georadius is O of n plus log of m. N is the number of elements inside the bounding box of the circular area defined by the center and radius in the query. And m is the number of items inside the geospatial data structure. So in effect, the more points you have in your search radius, the more costly the query. Now, for each query result, we also need to run the zscore command against the capacity sorted set. As you can see here, the zscore command has performance O of 1, which is as good as it gets. So as far as time complexity is concerned, we expect this technique to perform well. But we may want to put limits on the search radius if we expect the radius to contain thousands of data points or more. But there's another performance consideration here, and that concerns latency and round trips. Suppose that our georadius call returns 100 results. We then call zscore for each of those results, making a total of 101 round trips to the server. Last week, we learned how to use pipelining and Lua as a way of avoiding round trip costs. Let's start by looking at pipelining. Can we wrap all of these commands in a pipeline? Well, no, we can't. The reason is that we need an intermediate result. We need to get the result of the georadius command to pass to the zscore commands. So we can wrap the zscore commands in a pipeline, and this gets us down to 2 trips, one for georadius and another for the batch of zscore calls. If we want to take this a step further, we can put all this logic into a Lua script. The advantages of this are, 1, there's only a single round trip to the server. 2, we're not returning any georadius results that will ultimately be filtered out. And 3, this code can be reused across applications if necessary. Now there's a single Lua script that encapsulates all of the logic for our geosearches. But there's also a disadvantage. Lua scripts run atomically, so our script will block other commands while it's running. This isn't a problem when georadius returns a small number of results, but if we expect a large number of results, perhaps in the thousands or more, then the pipelining approach I just outlined is the better solution. So what have we learned in this unit? First, we learned a technique for adding criteria to our geoqueries. We have a set or sorted set whose membership indicates a property we're interested in. In this case, the set represents capacity. We then check each geo result against the set. Next, we reviewed the performance considerations for this technique. We looked at time complexity and round trip time. Finally, we saw how to mitigate round trip time using both pipelining and Lua. In the next challenge, you'll add support for the solar site capacity plus GeoQuery to the app.